All right, so now that we've gotten through some of the introductory biology disciplines and scientific method, it's time to talk about sort of really what all biology is based on. So we're going back to the, as fundamental as you can get. And we have to talk about, how living things operate. Well, living things are really no different than non-living things as far as what goes on inside their bodies, as compared to what's going on in, say, like an inanimate object. So, all living things, as well as non-living things, are abiding by chemical laws all the time, right? So, how atoms bond together, how they split apart, how they change with temperature, that kind of thing. Chemistry also abides by physical laws. So the reason that you learn physics and chemistry in high school is to kind of like get you prepared for understanding how, well, the world works really, and living things are no different. Okay, so physics, basically, for an example on how to apply it to living things would be forces in or placed on the body. So that would be like how joints move. For sports medicine, how liquids move in a closed system like blood pressure, how electricity is conducted like conduction. Chemistry, of course, is, the root of all physiology, how living things actually operate on a chemical level, right? Pharmacy, what drugs do to a particular system under disease or not. Anesthesia, growth and repair, all of these things are really how biological organisms operate. So the outline for this slide, or sorry, this presentation, I'm not really going to go over all this, but this is what you're in for. You can read that yourself. And we're going to go from 1 to 4. So matter consists of chemical elements in a pure form. Let's start with the basic, most basic of basics here, really. Um, and you should know that matter can either be elemental, which means it's a pure substance, right? Can't be broken down by any other substances, or it can be a compound, which means that you have multiple types of elements that are bound together in a fixed ratio. So that would be, things that aren't elements, but obviously are still made up of matter. So to give you an example of that, what we're looking at here is well, two elements and then one compound, right? So sodium is a metal. Actually, it's an extremely soft metal, and you can see in this picture it's being cut with a knife. And it's highly reactive. It's in that first column of the periodic table if you remember your chemistry. It really really wants to bond with things. Okay. It has one electron in its outer shell, which makes it extremely reactive. Now, the second column here is chlorine. Chlorine is a poisonous green gas that has 7 electrons in its outer shell, which means it also wants to bond with things and is highly reactive. Okay, so now you have sodium, which is a reactive metal, actually can catch on fire if you put it in water. Chlorine, which if you breathe it in, it's so reactive that it can react with your tissues and cause harm. This is basically what mustard gas was back in World War I and killed a bunch of people. If you put this dangerous metal and this deadly gas together, you get sodium chloride, right? Which is and actually kind of essential to our diet, right? We need a certain amount of salt in order for the body to work well. So what this shows you is that, even though elements may act completely differently when they're separate, when you bond them together, they have completely different properties, right? So sodium chloride, obviously, it's in everybody's kitchen. Gives food a little bit more flavor, and we use the elements in sodium chloride once they're in our bodies for essential functions. So, I think it's important to understand that every one of these will have different properties, the elements by themselves or the compounds that are made from them. So the essential elements for life. So, we go down that periodic table, which was drilled into your head in chemistry. I imagine you had chemistry at least in high school, right? Out of all those elemental formula or symbols that you needed to memorize, only about 25 of them are really essential for life. The big majority of those would be carbon, hydrogen, oxygen, and nitrogen. That makes up about 96% of living matter. Okay, and we'll talk about the compounds that use these elements a little bit later. Most of the remaining 4% consists of calcium, phosphorus, potassium, and sulfur. These are what we call micronutrients or nutrients that can occur in the body and are also essential for life. We just don't need as many of them. Trace elements are those that are required by organisms in extremely minute quantities, and sometimes organisms can actually get along without them. So Here's an example of what I'm talking about. Now, obviously, over on the left picture here, you can see this row of corn plants that this man is standing in front of is relatively stunted, as is the field to his left, right? Um, the corn to his right is growing really, really well. It's about twice the size or so of the plants that you see in the background. Why this is because the corn to his left on the right of the picture have a nitrogen deficiency. So what that means is because nitrogen is essential for life, these corn plants, as they grow, didn't have enough nitrogen and therefore weren't able to add as many cells to their bodies, right? Plants have bodies too. What you see over here on in letter B is an iodine deficiency. So this woman, what you're looking at in her neck is called the thyroid gland, and it makes thyroid hormone, which is essential for living things to maintain metabolism. Well, if you don't have iodine, I'm not going to get into how thyroid hormone is made, but iodine sort of like completes the formula for thyroid hormone, this essential hormone that your thyroid gland produces. If you don't get enough iodine, your thyroid gland is literally going to store what it makes because it doesn't have the final ingredient, this iodine, to really complete the formula, and it's going to grow bigger and bigger and bigger. And we call this condition a goiter. Goiter, if you want to look it up. So, unfortunately, this woman would have a normal physiology. She wouldn't have this big thing in her neck if iodine was available to her. But because probably where she lives, she just doesn't get it in her diet. So it just shows that, you know, really essential elements like nitrogen have large effects, but even some smaller, sort of like micronutrients, they also have potential long-term effects. So, an element properties depends on the structure of its atoms. We're going to get back down into chemistry just a little bit. We're not going to go anywhere near as in depth as your chemistry class. So each element consists of atoms. An atom is the smallest unit of matter that still retains the property of that element. So it'll behave like the rest of the element that it came from, right? Atoms are composed of subatomic particles, including neutrons. They are in the nucleus and do not have an electrical charge. They're neutral, which is what gives them their name. Protons, also in the nucleus, they have a positive charge, and electrons, which are spinning around the nucleus really, really fast, they are what give atoms its negative component of its charge, right? So they would be negatively charged. So neutrons and protons, as I said before, keep in mind they're in the nucleus. They also give the atom most of its mass. Electrons form a cloud around the outside of the nucleus, and they're spinning around super, super quick, as you can see in these two models. Now, this is kind of what I guess you would a little bit more realistic model over here in letter A. This cloud of negative charge here, these two electrons, that's all the electrons and where they occur around the positive and neutral nucleus, right? Now, if you look over here in B, those two positive components, the protons and the two neutrons, are together in the nucleus. And really what this is just showing is more like a schematic or artistic representation where you have the two electrons floating around the outside. So what element is this? Yep, you're right. It's up in the title, actually. It's helium atom. Okay, so neutral charge, not very not reactive at all with anything. Okay, so the atomic number and the atomic mass are really actually pretty often, they're confused, right? So atoms of the various elements differ in the structure of subatomic particles. So those are the ones in the nucleus that add to the mass, as I said before. So an element's atomic number is the number of protons present in one atom. Okay, so that's just the protons, half the mass really, or even less sometimes, or even maybe a little bit more. But that's just counting the protons, because protons can vary. An element's mass number is the sum of protons plus the neutrons. Neutrons and protons actually have a little bit of mass to them, and that gives the atom the huge majority of its total mass. The electrons really don't weigh very much. It's negligible, really. It doesn't even really make sense to count the electron mass. So the atomic mass is the number of neutrons versus the number added to the number of protons. So that can be pretty much approximated by this. So I just want to make sure it's clear in case I was confusing here. Atoms are defined by the number of protons that they have, right? So if you have 2 protons, you have helium. If you have 1 proton, you have hydrogen. 3 protons, you have lithium. Um, Now, the number of neutrons, however, can differ, and we'll talk about that in a second. But the proton number, that's what defines what element it is. Isotopes are where you have differing numbers of neutrons. Okay, so as I just said, remember, they must have the same number of protons. Most isotopes are naturally occurring and stable, but some are actually radioactive, which give off particles and energy. And we've learned, well, how to avoid these things because they can be really dangerous for us. But we also have learned to utilize them for imaging and as tools, to help us explore different biological systems. So when these isotopes undergo radioactive decay, so the ones that actually break down radioactively, they lose different particles depending on the type of radioactive decay, and sometimes they're even changed into a different element. So, like plutonium comes uranium, like the really um, high energy radioactive isotopes. So, most of the time, I don't really want to play with radiation, not knowing what I'm doing, right? Most of the time, we think of radiation as a bad thing. It is a carcinogen, which means if you're exposed to too much radiation, whatever form it occurs in, it can cause cancer. For your age group, I imagine pretty much all of my students are, in your 20s, right? For your age group, the most common form of cancer would be skin cancer, right? So the ultraviolet light, which is a form of radiation from the sun, if that hits your skin in too often and too high in intensity, it can change your cells to become cancerous, and that's obviously not what you want. So, how can we actually use isotopes, these radioactive elements, in a good way? How can we use them to help us in biology? And that's what we're talking about here. So, what you see here is a scan of, somebody through their throat. You can see their nose up here and their chin, right? This is their epiglottis. And what you're seeing here is this person has throat cancer. How do we know that? How does this just light up on the scan, right? I mean, it's not like cancer cells are really much different than regular non-cancerous cells. Well, this person was given radioactive glucose. Okay, so if you think about it, you have to know a little bit about cancer to understand what's going on here. Cancer is cells that are growing way out of control, right? So you just have cells that are growing and dividing and growing and dividing, and they're not restrained by anything. So if you think about it, those cells should be using more resources in order to grow. Even though they're cancer cells, they still need fuel to grow, right? One of the primary fuel sources for cells and their growth is glucose. So if you could chart which cells in the body were using glucose the fastest, and above the other cells that are around it, you could actually determine which cells were cancerous. Well, how would we do that? We would just put in some radioactive carbon to make glucose, because glucose has carbon in it, right? Sugar has carbon in it. And what that leads to is cells absorbing that radioactive sugar faster than all the other cells in the body because they're growing fastest. So you do that, you wait a few hours, and then you do a scan. You can see where all or most of, anyway, that radioactive glucose went in the scan because it gives off energy. It's radioactive. And that will allow you to target the tumor. That's pretty cool stuff, right? So, if you have any symptoms and they really just can't pinpoint, where the cancer is, one of the things they can do is a scan. This is called a radionuclide scan, and that'll allow them to pinpoint exactly where the tissue is that might be of concern. Okay, so that was really talking about the nucleus here. Now let's talk about the electrons. The electrons are, I would say, for biology, probably more important to talk about because we're going to be thinking about them a lot more, and how they bond and how they form bonds a lot more than the particles that are in the nucleus. So keep in mind, electrons have energy states. Okay, so you could take an electron and hold it at a high energy level, or you could take an electron and hold it at a low energy level, right? And they can change, they can shift, right? So electrons that are holding more energy will be further away from the nucleus, that center nucleus that they spin around, than electrons that are at lower energy. And when a high energy electron gives off energy and goes to a lower level, it'll release that energy as some form that's sometimes detectable, light or other electromagnetic radiation. So that's going to lead us to our next video, which we'll start in a second.